Dear students, you are welcome to lecture number 14. In lecture number 14, we will be trying to understand how a singly reinforced beam can be designed. And in the previous few lectures, we have discussed details about the limit state methodology and what are the various parameters, what are the various formulas, properties which we have to take into account when we are going to design any problem. First of all, we learned how to do the analysis of singly reinforced beam, then doubly reinforced beam, and after that, we have gone through what are the various possible probable steps which we can follow when we are to design a singly reinforced beam. So today in this lecture number 14, design problem will be discussed and we will be using various steps, and based on the information which is available in IS 456, we will be going to discuss and do the complete design of a singly reinforced beam. Now first of all, we have to go through the statement part so that we can understand and just collect the information which is available with us before the design of the section, and based on that we have to take some necessary assumptions, and we may have to assume some of the information which is not available in the design statement. So first of all, it is mentioned in the design statement that a reinforced concrete rectangular beam is supported on walls 230 mm thick. So one thing is very much clear, that this beam section or this beam is a case of a simply supported beam, because this beam is supported directly on two walls, that means brick walls 230 millimeter thick, and these two walls are spaced at a clear distance of 6.5 meter. So clear span is given in the design problem, that is 6.5 meter. The beam carries a superimposed load of 9 kilonewton per meter. So live load is given, that means superimposed load of 9 kilonewton per meter is given. Beam is located in a coastal town. So location of the building is mentioned in the numerical in the design statement. And what we have to do, we have to design the beam section as per IS 456 2000 recommendation. And regarding tensile reinforcement, it is mentioned that tensile reinforcement may be taken as HYSD bars of FE 415 grade. So you may came to know that in this statement, exposure condition is mentioned and no dimension of the beam is given, either width of the beam or depth of the section. So that means we have to work out what should be the possible width of the beam as well as depth of the beam. And regarding steel, it is only mentioned that grade of steel is mentioned, so no diameter of the steel is mentioned. As well as very interesting part is that in this statement no grade of concrete is mentioned. So that means we have to assume the grade of concrete, diameter of tensile reinforcement, width of the section we have to work out, depth of the section we have to work out. And now how to assume or how to decide various information which is not available in the design problem. Let us go through step by step. So very first step is we have to do the selection of grade of concrete and steel. No doubt grade of steel is mentioned. So how to select the grade of concrete, because concrete is of various grades available, or you can prepare various grade of concrete. So which grade of concrete will be suitable, or what should be the minimum grade of concrete which is recommended by IS 456, that will be based on the exposure conditions. So what is the exposure condition? Now it is mentioned that beam is inside the building, and it is mentioned that it is located in a building, so it is not outside the building. That means it will be in the interior of the building, located in a coastal region. So from coastal region we can just work out what will be the exposure condition. But one thing which we have to note down, that maybe it is building is located in coastal region, but the beam which we are going to design, it is not directly exposed to the coastal environment. So we can take the information, we can tally the information available in code, and the various sections we have already discussed in the previous lecture. So based on this information which is available, we can say that exposure condition may be taken as moderate type of exposure condition. So minimum grade which is recommended by IS 456 may be taken as M25 grade of concrete, be based on the moderate type of exposure condition, and subsequently we can take minimum clear cover of 30 millimeter. Again, it is also based on the moderate, that means exposure condition. So in this step we have decided that we will be adopting M25 grade of concrete along with steel of that means high strength steel of Fe 415 grade we will be taking. So based on the information, because the grade of concrete as well as the minimum cover, clear cover which we have decided, that is based on the moderate condition, and that is based on the consultation with the IS 456. So we can say that this cover, 30 mm minimum cover, will be sufficient or adequate for normal durability requirements. Now step number 2. Here we have to fix the dimensions of the section and grade of steel. So how to fix the dimension? In statement we are already gone through that, only wall thickness is mentioned. No dimension of the beam section is given, so we don't have any type of compulsion. We can assume based on our experience. So first of all, let us assume that the width of beam is 250 mm. So we have assumed the one dimension, that is width we can take 250 mm, or either we can take 300 mm. And since the span of beam is lesser than 10 meter, because clear span distance is 6.5, and what will be the effective span, that later on we will be going to calculate. So based on the clear span, since it is less than 10 meter, so based on the IS code recommendation, where we are considering the deflection criteria, so L by D ratio we can take equal to 20, because it is a case of a simply supported beam. So again, now L by D when we take it equal to 20, so from this we are able to get the just judgment, or we can able to assume that D 325 mm, this will be the minimum value. So minimum effective depth required is 325 mm. How it is? It is based on the deflection criteria. So we are assuming that as per IS code, if we are assuming the dimension based on the deflection criteria, then it is expected that your beam which you are going to design will behave safe in case of a deflection. So making a round off, we are providing 350 mm effective depth of the section. So again, now since the grade of steel is mentioned, so we are starting with our first trial, that is by adopting 20 mm dia bars as tensile reinforcement, and 8 mm diameter we will be taking for vertical stirrups. And the clear cover we have already discussed, that we have assumed clear cover equal to 30 mm. So what will be the overall depth of the section? That we can calculate from this formula, and because this d is overall depth and small d is effective depth of the section, and phi will be the diameter of the main reinforcement. Now you can you just note here that we are going to design only singly reinforced section. So steel will be provided only in the tension zone, and phi s we can consider as the diameter of the stirrup. Cc we can use this abbreviation for cover, that is clear cover. So by putting all the values, it is required that overall depth will come out to be 398 millimeter. So again, rounding off, we can just adopt capital D, that is overall depth of the beam is equal to 400 mm, and effective depth we can take 350 mm. So accordingly there will be the adjustment of the cover. Now step number 3. This is also very important. In one of the previous lecture I have discussed why effective span calculation we are doing. So the information which is available in the code, based on that recommendation, effective span when the beam is simply supported. So there will be two type of conditions. So very first condition is effective span. We can calculate by adding effective depth to the clear span. So it comes out to be 6.85 meter. And the second condition is we have to measure the center to center distance from the supports. So that will be coming out to be 6.73. So we have to take the least value. So L effective or effective span length we will be taking into consideration during all the calculation, that is 6.73 meter. Now step number 4, here we are going to decide what will be the various type of loads, as well as based on that load values what will be the bending moment and the shear force. So step number 4 will be devoted to the calculation based on the load as well as bending moment and the shear force. Now first of all, very first step is we have to calculate the self weight of the beam per meter length based on the dimensions which we have already assumed, and sometimes it is also known as dead load. So WDL we can say it is dead load of the beam section per meter length. So this is 1 meter into 0.4 will be the overall depth of the section, 0.25 will be the width of the section, and 25 will be the unit weight of the reinforced cement concrete. So based on this calculation we are able to work out that this will be equal to 2.5 kilonewton per meter. So here we can say that we have assumed if any type of finishing is there. Generally in case of beams, finishing load is not considered, but still we are just writing here that it is already assumed that if any type of finishing is there, so then that load of finishing is already included. So total dead load we can say per meter length is 2.5 kilonewton per meter. So you can just take into account if you find any calculation error, that you can rectify later on yourself. Now regarding the live load on the beam, so live load on the beam is already mentioned in the numerical. So here you need to make it a correction, it is a 9. So W live load is taken as 9 kilonewton per meter, and so adding these two, total load which will be just like UDL, uniformly distributed load, because we are taking dead load as well as live load having unit kilonewton per meter. So 9 plus 2.5, it is 11.5 kilonewton per meter. Now what will be the design load? So here you have to take the partial safety factor for loads, and so that partial safety factor we are taking here 1.5. So accordingly, when we multiply this with the total load, total UDL, so WD here means design load on the beam section, and that design load having of intensity, that is 17.25 kilonewton per meter. Now, since it is a simply supported beam, so maximum bending moment will be at the mid of the span, and the formula is WL square by 8. So from this formula, we are able to calculate what will be the factored bending moment which will be coming on the beam. So factored ultimate bending moment, that is equal to 97.66 kilonewton meter. So that means when you put the value here, and you will get the after calculation mu is equal to 97.66 kilonewton meter. And similarly, we can just calculate a factored ultimate shear force, and we know that if there is a simply supported beam and load is in the form of a UDL, uniform distributed load, then the maximum shear force will be at the support level. So maximum shear force we can calculate WL by 2, that is 58.04 kilonewton. Now we are we have calculated what will be the load on the beam, what will be the ultimate bending moment, what will be ultimate shear force. Now in step number 5, we are going to start by doing the calculation in the form of various type of checks. So let us first of all check what will be the XU by D ratio, because based on that XU by D ratio, we will be able to decide whether it is a balanced section or over reinforced section or under reinforced section. So type of the section, type of the stresses criteria, we will be able to understand. Now we can use this equation which we have already discussed in the previous lectures, that XU by 2, XU by D we can just work out by putting all the values. So after putting all the information which is available, MU we have calculated, depth we have decided, width we have decided, grade of concrete is M25, and based on putting all the values, we will be able to find out that XU by D ratio is coming out to be 0.433. So here XU by D ratio 0.433, and it is less than XU max by D ratio which is available in the IS code, so that is 0.48. So 0.433 is less than 0.48, so we can just say here that section will be under reinforced. So we can start with the other calculation because it is okay as per the IS 456 guidelines. Now what is step number 6? Here we have to calculate the required area of tensile reinforcement. Now one thing you have to be very clear here, that when we are going to decide the area of steel required, so area of steel will be directly depend on the what will be the movement of bending moment. That means what will be the bending moment coming on the section, because that due to that bending moment there will be the bending effect, and due to that bending effect your beam will be subjected to compressive stresses as well as tensile stresses. So as per previous discussion, we already know that why we are providing tensile reinforcement. So tensile reinforcement is to take care of the tensile forces which are coming in the beam section. So major effect is due to the loading, and that loading in the form of a bending moment. So in a very simple language we can say that if the bending moment of the section is more, then we may require more area of tensile reinforcement. So how to calculate area of tensile reinforcement? So here we can use this formula directly, and after putting all the value of Fy, value of Xu which we have already calculated. So here Xu value you can get from this formula, that means Xu is equal to 0.433 into D, and D we have already decided 350 mm. So XU you can get from this formula, and you can put all the values, all the information available in this equation. We can say this is equation number 1. So you are able to work out that how much is the tensile steel area required, tension reinforcement area required. So that area after doing the calculation is worked out to be equal to 942.66 millimeter square. So up to this step we have decided what will be the dimensions of the section, what will be the grade of the concrete, what will be grade of steel, what will be the diameter of the tensile reinforcement, etc., etc. So you remember that in the very first two steps we have decided, or we have assumed, that we will be taking 20 mm dia of a tension reinforcement. And now this 20 dia tension reinforcement should be such that it should be able to give at least AST, area of steel, equal to 942.61. So based on this, we have decided that number of 20 dia bar required, how many bars are required, that will be easily you can find out by dividing area of steel which is required, AST required, divided by area of one bar. So here area of one bar mean cross section area of one bar, and you are aware when we are talking about the bars, so then bar will be like this. That means it is cross section area will be just like a circle. So based on that you can find out the area of one bar, and the formula you can use area of one bar is equal to pi by 4 into d square. So based on that, area of one bar of 20 dia, it worked out to be 314, and the total area which we have to provide, that is equal to 942.61. So dividing this, you are getting 2.9. So we say approximately that we will be providing three number of bars as tensile reinforcement. So here we have noted down that we will provide three numbers 20 mm dia HYSD bars as tensile reinforcement, and but here what you have to do, you have to apply a check for what should be the minimum area of tensile reinforcement recommended by IS code. And after going through the calculation from the IS code, you are able to find out that how much is the AST minimum required. So based on that formula, you are able to find out AST minimum, and you can compare that AST minimum is quite lesser than AST required, which we are going to provide. So we have provided three number of bars which will be giving AST quite greater than AST minimum. So we can proceed with the other part of the design, because it is okay, it follows the guideline of the IS code. Now step number 7, that is shear reinforcement, which we talk in the terms of shear stirrups, and whether it is vertical stirrups or inclined stirrups. So very easy to just execute the construction of any simple RCC beam, etc. So we can start with vertical type of stirrups. So when you refer clause number 22.6.2, where it is mentioned that critical section for shear, so that means where you have to find out the shear requirement, shear stress. So what will be the shear stress at a section which is termed as critical section? So critical section for shear is at a distance of effective depth, that is effective depth of the member from the face of the support, and from this distance up to the support we can consider that shear stress is same shear stress. That means whatever be the shear stress coming out to be after calculation at a critical section, and we will be able to work out that based on that value of shear stress at that section, we have to provide the shear reinforcement, and that shear reinforcement we can provide up to the support considering the same value of the shear force or shear stress. Because you may be aware that when there is a simply supported type of beam having some UDL, and when you draw the shear force diagram, then your shear force diagram will be somewhat like this. That means maximum shear stress here at the support, but after that it is constantly decreasing. So when you are taking, let you take section somewhere here, that means at some distance d from the face of the support. So what will be the shear force here? Based on that, we have to design the shear reinforcement. That means the shear stirrups will be designed based on this information. Now you can go through this diagram and okay, let me remove these for more clarity. Okay, so okay, now you can see here this is a just a simply supported beam, and here it is supported, and from let this is the face of the support basically, and at a distance that is equal to effective depth of the beam, we have to take a section. This will be the section, and this section will be known as the critical section. So at this critical section you have to find out what will be the shear force, and based on that shear force you will be able to find out the shear stress. So shear force at a distance, that is at a distance d from the support. So how that you can go through this diagram, that this is a beam which is we are going to design, and these are the supports, that mean brick walls. So this black color, dark black color line show the beam, and on this we have just loaded this beam with the UDL, which we have already calculated at 17.25 kilonewton per meter, and this was the clear span. So based on the theory of structure analysis, you can easily work out the reaction at the support level, center of support. So that reaction is coming out to 58.04. This will be the maximum shear force, and this maximum shear force will be at the center of the support. And what we have to find out, we have to find out the shear force at this dotted line showing that is the critical section, and this critical section is at a distance, you can say this is the face of support, so this will be the d distance, but we are taking distance from the reaction part, so that's why this distance will be equal to 0.35 is the uh, effective depth of the beam plus half of the width of the support, so it comes out to be 0.475. So what we have to do, we have to find out what will be the value of shear force at this section. So after doing the calculation, we can work out that shear force, which is known as nominal shear force, we can say. So nominal shear force at this section, that is a critical section, it works out to be 49.85 kilonewton. You can just see here at the center of the support, shear force was 58.04. But as you move away from the support, your shear force is getting decreased. So we have to design whether as per the IS code information, shear stirrups or shear reinforcement for this particular value of shear force. So based on this value, that shear force, we can work out what is the nominal shear stress. So nominal shear stress, that is tau v. And tau v is VUY BD, shear force by area of the effective area of the section. So it comes out to be 0.57 Newton per millimeter square. Now this is the shear stress at a section, critical section. Now we know that our concrete is also able to take care of shear forces along with the compressive forces, shear forces. So that means we can say our section where we have provided concrete as well as steel. Now this is the section, here you will be providing some steel and the other portion is of concrete. So concrete is very good in compression, as well as it can also carry some capacity, has some capacity to take care of the shear forces. So now we have to refer the IS code guidelines, and to work out the IS code guidelines, first of all we have to understand that what is the percentage AST we have provided. That means percentage of steel which we have provided at the support level. So AST, we know that it was something 942 something, and V was 250 mm, and effective depth was 350 mm. So this will give you the value 1.077. So this is the percentage of steel which is we are able to provide at the level of the support. So you can refer this table number 19, which is given in IS 456, and I have just taken a snapshot out of it because our case area of percentage area of steel is 1.007. So based on this, you can check, because R 1.00077 will be lying in between these two limits, that is 1.00 and 1.25. So based on here, you will be able to find out here what is the grade of concrete. So based on the grade of concrete, which is M25, you can just find out what is the value of the shear stress, and due to this steel as well as concrete for 1% steel and 1.25% steel. So based on these two values, we can work out what will be the value of the shear stress taking capacity of concrete, and that is based on the 1.00077 percentage of steel. So we can do the interpolation, and after getting interpolation, this is table number 19. Percentage of steel is 1.007, and grade of concrete is M25. So after doing the interpolation, we are able to find out the design shear strength, that is tau C, due to concrete. Design shear strength carrying capacity of this section is 0.658. Now you can just compare this value with this nominal shear stress value. So the design shear strength based on the grade of concrete and area of steel is greater than nominal shear stress. So that means design shear strength tau C is 0.658, and you can say that tau C is greater than tau V, and tau V is the basically the action part, and tau C is the capacity of the section. So no design shear reinforcement is necessary. But code is suggesting that we have to provide minimum shear reinforcement, whether design shear reinforcement is not required, but still you have to provide minimum shear reinforcement as per clause number 26.5.1.6, and let us go through it. So based on that information, based on this clause 26.5.1.6, we are getting this equation, that is ASB upon BSB greater than or equal to 0.4 by 0.87 Fy. And what is ASB? ASB is the basically area of the stirrup. Now we will be deciding that we will be providing two-legged. So you can say two-legged vertical stirrups. So when there are two legs vertical stirrups, we have to find out what will be the area of the one ring, you can say, of stirrup. So it is diameter which we have decided for stirrup is 8 mm. So pi by 4 into 8 square will be 50.26, but it is of two legs, so area will be 100 in 0.52 millimeter square. Fy, you know that 415 based on the grade of steel which we have decided, and so after calculation from the based on this formula, we are able to find out that the spacing between the stirrups, SB is the spacing between the stirrups, it should be less than equal to 362 mm center to center. But here code is also restricting the maximum spacing of shear reinforcement. So code recommendation or code restriction about the maximum spacing. Now what code is suggesting in clause number 26.5.1.5 regarding the maximum spacing of shear reinforcement. So code is saying it should be least of the following. So first is 0.75D. So 0.75 into 350, that is 262.5, and in no case it should be more than 300. So we have to pick the least value out of these two. So it is 262.5, and here equation A is giving you spacing between the stirrups should be less than 362, but based on this condition we can't go beyond 262.5. So we have to provide spacing between the shear reinforcement should be even lesser than 262. So you can see here in this diagram, this is a section of a beam, and you can see there this is a hanger bar, this is the main steel which we are providing, and these vertical rings, they are known as the vertical stirrups. So now when we are talking about the spacing, so spacing between these two vertical rings, so this will be your SV, which we have worked out. So when we are going to decide that what will be the spacing between the shear reinforcement, so we have decided, let us provide two-legged 8 mm dia stirrups at 250 mm center to center. So it is less than 262. So every check is okay now. So we can provide shear stirrups of two-legged 8 mm dia at a center to center spacing 250 mm throughout the length of the beam. So here this will be 250. So accordingly, after every 250 mm, you have to provide this ring. So this will be provided throughout the beam section. Now step number 8, here we have to check for the development length, whether the section which we have chosen and the steel we have selected or we have provided, it is able to provide sufficient development length or not. So that we have to check. So we have to refer clause number 26.2.1 of IS 456, where it is mentioned that the development length LD, which is given by this formula, already we have discussed in the previous lectures. So what is the phi, what is sigma s, what is tau Vd. So for M25 grade of concrete, this tau Vd, that is bond strength of the steel with the concrete, is 1.4 Newton per mm square. But again, it is mentioned in the code that if you are providing deformed bar, because this value 1.4 is only for plain steel bar, but we are providing high strength bars, deformed bars. So for deformed bars, which conform to IS 87786, and whenever we are obtaining any deformed bar in the market, that is manufactured based on the guideline in 1786. So what we can do, instead of plain bar, we are providing deformed bars. So we know in case of deformed bar, bond strength will be higher. So we can just increase this bond strength, which is given for plain bars, by 60%. So that means tau Vd value will be higher in case of deformed bars. So taking more than 60% extra, tau Vd is coming out to be 2.24 Newton per millimeter square. And after putting all the value in this formula, we are able to get that LD is required is 806 millimeter. Now what clause 26.2.33 and part C is saying, let us go through the statement. At a simple support, that means simply supported beam, at a simple support and at point of inflection, positive movement, tension reinforcement will be limited to a diameter such that LD calculated or computed for FD should not exceed this formula. So here this part of the statement is applicable, and what is point of inflection, that we will be later on going through the design problem. So here this subclause part C is applicable in our case, in case of a simply supported. So we have to check whether this LD which we have already calculated is exceeding this value or not. Now what is M1, what is B, what is L0? Let us try to understand. So as we have already written M1B by B plus. Now this value of M1 by B can also be increased by 30% when the ends of the reinforcement are confined by a compression reaction. So that means L by D should be less than or equal to 1.3. We have multiplied by 1.3 of M1 by B. That is mean 30% extra we have considered. So 1.3 M1 by B plus L0. Now let us go through step by step for each value. Now what is M1? M1 is the moment of resistance in the section by assuming that all reinforcement at the section to be stressed to FD, that is the maximum stress. And what is FD? Design strength of the steel, that is 0.87 Fy in case of limit state design. So we are that's why we have taken only this part of the statement, because we are designing it by limit state method. Now what is V? V is the shear force at the section due to the design loads, which we have already calculated. Now third remaining part is L naught. L naught is the sum of the anchorage beyond the center of support and the equivalent anchorage value, etc. But we are more concerned about this statement, that it is L naught is limited to the effective depth of the beam or 12 times of the diameter of the bar, whichever is greater. So here we are able to calculate this value, since we are providing three number of bars, and let us assume that we are taking these three number of bars within the support. So three number of bars are available at support section. So area of these three number of bars is 942 millimeter square. Fy is 415 Newton per millimeter square, and XU, as already told in the previous slides, that XU is equal to 151.55 millimeter. So by putting all the information, we are able to get the value of M1. It is 97.59 kilonewton meter. We have already calculated 58.04 kilonewton, and L naught. L naught here code is suggesting that greater of the 12 dia. 12 dia mean 12 into 20, that is 240 mm, or effective depth 350. So whichever is the greater value. So that's why L naught we can take 350 mm. And by putting the information in this formula, LT is 806 mm. Let us check whether it is less than or greater than or equal to. So by putting value of M1 here, value of V here, as well as L naught, so we are getting 2.535. So it is very much clear that LD 806 mm is less than 2.535. So we can say here that this check for developmental length is also correct. It is okay as per the guideline of ISO 456. Now, last important aspect of any design problem is the reinforcement detailing, because whatever we have done up to 8 steps, that will not be taken away at the site. At the site, you will be providing the detailed of the reinforcement for the execution work. So that is based on, you have to draw a diagram in which maximum details available with you, you can put on the diagram. Now let us go through step by step. First of all, this is a beam which we have decided to design. This is the beam, and this is a simple support both sides, so beam is a simply supported. Clear span length is 6500 mm, because as per terminology we don't write units. It is already written in the drawing, in the corner of the drawing, where we are putting all the details, that all the dimensions are millimeter. So we can write here 6500 only, or 6500 millimeter. So this is the clear span. Now you can see here we have shown a steel bar at the bottom, and it is a dark color ball. And what is this? This is 20 mm, the 20 mm dia, three number of bars which are provided. So this will be the tension reinforcement, which is shown as a black colored line. And at the top you can see another bar, and this bar will be, you can say this is two number of hanger bars, or hanger bars, that is two bars we are providing. And this red color will be the shear stirrups which we are providing. Now here, this one is the section. You can take a section. Suppose we are taking section somewhere here. So this will be the sectional view, and this 250 is the effective depth of the section. 400 mm is the overall depth of the section. Now, three number of bars you have provided. You can just show here more information as well as clear cover, effective cover, etc., effective depth. So whatever. But here we are showing that three number of 20 dia bars. These are the main reinforcement, which is also known as tensile reinforcement. And this red color ring, this is a shear stirrup. So we have provided two-legged 8 dia stirrup at a 250 center to center throughout the beam. So that means this is one stirrup, this is another stirrup. So this distance is 250 millimeter. So throughout we are providing this, but since near the support shear force is greater because we have taken critical section at a distance d from the face of the support. So like this. So as the shear force at the center of the support is even greater than this value, so you can do one thing. You can reduce the center to center spacing of the bars within the this region where support is there. So you can provide it. It may be at a 150 center to center or 200 center. But throughout the beam, shear stirrups are provided at a spacing of 250 center to center. So these are two leg stirrups. Two leg stirrups mean you are providing this. This is one leg, this is another leg. This type of stirrups which you are providing. So they have their own importance. So this much information at least you have to provide in your reinforcement detailing drawing. So you can go through some more numericals from some reference books for your practice purpose. Thank you.